Okay, so welcome everyone to this session of YR Rounds. Today we have with us Umang Mathur, who is a fifth year PhD student at UIUC. Umang's areas of interest are pretty much in programming languages, verification, automata theory, logic, games. So Umang is going to defend his thesis very soon in September, and he'll have a short stint with Facebook. After which, in fall 2021, he'll be joining NUS as an assistant professor. So thank you, Umang, for joining us. So before I hand it over to Umang, just the usual set of announcements. So this talk is going to be recorded, and please consider keeping your video on because it gives all of us a feeling of a physical talk. In case you wish to ask a question, you can use the raise hand feature. And unless you ask a question, you are not going to be recorded, even though the talk is going to be recorded. I think that's pretty much the announcements we have to make. So Umang, it's all yours now.
Thank you, Krishna. So can you remind me at the 15-minute remaining mark?
Absolutely.
Yeah,
Yep.
sure.
Yep.
Okay. Thank you.
Yeah.
So I'm going to be talking about uninterpreted programs. With Madhusudan Parthasarthi and Mahesh Vishwanathan, who are professors at Illinois. And this talk is based on works that appeared in Popple 2019, and one of them is going to appear in Tarcast 2020. So let's start. Well, as we all know, program verification is undecidable in general. And while we do know of decidable classes, most of these either do not have loops or recursion. So these are like straight line programs, or they work over variables which come from finite domains, so much like Boolean programs. Or we do have models like Petri nets for which we do know of decidable questions. But then things like Petri nets, which have counters and you can only decrement and increment and not check for counters, that's not a very natural way to model programs. And so today I'll be talking about a class of programs which in fact meets all of these criteria. And so it is going to be pretty expressive as a programming language, and it's going to have loops and recursion, and the variables in the program are going to work over infinite domains. So I'm going to be talking about uninterpreted programs in this talk. So what are uninterpreted programs? So these are programs where the functions and the constant symbols that are used in the programs are what we say uninterpreted or completely uninterpreted, meaning that there is no prior interpretation to attach to these symbols. So these programs are meant to work over arbitrary data models or first order structures. And these data models are the ones that give the semantics or interpretations of these symbols. And that is how you define the values of each variable at every point in an execution. And I'll be talking about these things in more detail. And on an intuitive level, if you have an assertion in such a program, that assertion is set to hold if it holds for every data model on which the program works. So let's look at some more details. Let's look at the syntax of these programs. So the way we formalize this as follows. You first fix a finite set of variables V. Okay, these are meant to be global variables. And then you also fix a first order vocabulary, which consists of the constant symbol C, functions F, and set of relations R. Okay, and now your programs are the syntax is that of any regular imperative programming language. So you have assignments. So C here is a constant and X is a variable. Similarly, you also have assignments to variables, from variables to variables. You can also assign F of a tuple of variables to a variable X. You also have if then else statements, while loops. You also have the special statement called assume, which essentially blocks executions if a condition is not met, and sequential. And conditionals are Boolean combinations of either equality atoms, so X and Y are variables and C and D are constants, or relational atoms. And so R here is an uninterpreted relation. Okay, so let's look at this example here. This is basically a list search program which traverses a list from X to Y, and at each point checks if the key associated with that node is some particular key K. And if so, it sets a Boolean flag to be true. Okay, so here T and F are uninterpreted constants. And the functions key and n, which are used to model these pointers, these data fields, are also uninterpreted. So now let's look at, so I'm going to now define the semantics of these programs, and to understand that we should look at executions of such programs. So executions here are basically sequences of basic statements. So these basic statements are either assignment statements or assume statements. Okay, and when you have a program, you can compile it down to a regular language, which is basically the set of finite executions of that program. So for example, if you just have a singleton program, it's going to compile down to essentially that statement. So exec of x is assigned y compiles down to the letter x is equal to y, x is assigned y. Similarly, exec of assume c is this singleton set of a string of length 1, which is assume of c. Now, if you have an if then else, you compile it down to a union of two languages which correspond to the two branches taken. Similarly, if you have sequencing, you have concatenation of languages, and while loops give rise to cleanest R. Okay, so let's now define the semantics. So as I said before, semantics of these programs are defined in terms of a first order structure on the same vocabulary as that of the program. So at any point you can associate values to the variables, where values come from the underlying data model or first order structure M. So, and this is defined inductively in a very intuitive fashion. So basically in the beginning, you look at, so in the beginning, so for every variable X, we assume that there is an associated constant X hat in the vocabulary. And so the initial value of these variables is basically the interpretation of that constant in that model. And now when you assign, you basically look up the function f, and you look up the previous values of these variables even through zr, and then you assign the resultant value to x here. Now let's look at what it means to say that an execution is feasible. So that's also pretty intuitive. It basically says that if you have assumes in your executions, then each of these assumes are met. Okay, so when you have a data model, each of the expressions inside the assume are going to have concrete values from the domain, and you basically check if each of these conditions are met. So for example, if you are looking at an assume c at the end of sigma, then if c is of the form x equal to y, then you must say that the value of x after sigma and the value of y after sigma in the domain are basically the same. And the rest are also pretty much the same. Okay, so in the rest of the talk, I might not refer to relations because there's a very easy way to model relations and functions. And I might talk about relations somewhere later in the talk. So let's talk about what it means to verify such a program. Okay, so we're going to talk about assertions or post conditions, which are going to look like this. Basically, these are again Boolean combinations of either equality atoms or relational atoms. Okay, so we say that a program satisfies this assertion phi if for every execution of this program and for every first order structure in which this execution is feasible, it must be the case that phi holds at the end of the execution in the model. So by this I mean that you replace all the variables in phi with the values of these variables in M, and whatever formula you get, that should be true in M. So that is what the verification question is. So you have possibly infinitely many executions in your program, and you look at each such execution and you check for each model in which this execution is feasible, whether or not the assertion is true at the end. So not surprisingly, the verification problems for even uninterpreted programs is undecidable. Okay, so before I move on, let me sort of clear one question that comes often. Why study uninterpreted programs? Well, one, because they are a very natural way to abstract your program. So your program might have interpretations like associated with symbols like plus and less than, and you can abstract them and think of it as an uninterpreted program where there are no specific semantics to plus and less than. And if you can prove that it is correct, then it means even with the specific interpretations, it's going to be correct. There are also other domains which are naturally uninterpreted, such as if you want to verify programs that manipulate heaps. So I already have one example that I've shown you, which was searching a list for a key. So there, the functional the pointers in your list like next and key are naturally uninterpreted. You can think of them as uninterpreted because you really want to check if all interpretations to these next pointers and key pointers are basically are allowed. Okay, so uh, so we've seen that verification of uninterpreted programs is basically an undecidable problem. So I'd like to ask the question, how do you verify a single execution? Okay, so here I have an execution of the same program that I've been working on for some time now. So it's a sequence of assumes or assignments, and you have this assertion b equal to true implies key of r equal to k. Okay, so if you have such an execution, you can cast it as a verification condition. So, and that pretty much looks like the execution. So you have a constraint for every statement in the execution here. So t assume t not equal to f basically translates to the constant t not equal to constant f. Similarly, the variable b is assigned f translates to the first copy of b, which is b1 is equal to f. Similarly, this assume translates to x0 not equal to y0. Okay, and so if you look at this b, this statement b is assigned true, it translates to the second copy of b, which is b2 equal to t. And so it's a fairly straightforward way to translate executions to verification conditions. And so you say that this constraint implies the assertion, and that is how that is how you would translate an execution to a formula. So the verification question for an execution would basically be to check if this execution, the assertion holds at the end of execution in every model in which this execution is feasible. And so it's easy to see that the execution meets the assertion if and only if this formula on the right, which is the verification condition, is valid in the theory of uninterpreted functions with equality. So, so this theory basically is on a signature of functions and equality, and you can ask whether a formula written over ground terms is satisfiable or valid, and that is the theory of uninterpreted functions with equality. Okay, so verification of a single execution can be reduced to checking validity of a quantifier-free formula in this theory, and this can be decided, in fact, in polynomial time when your assertion is true, which using this very nice algorithm called congruence closure. And so where is the gap? The gap is because a program may have infinitely many executions, and that is why verification of programs as such is undecidable, even though you can verify a single execution. So how do you recover decidability? Well, that's what I'm going to talk about in this talk. We're going to talk about a class of programs called Coherence. And the way this class has been designed is to ensure that you can perform this congruence closure in some streaming fashion on an execution. And I'll talk about all of these in a moment. So just to recap what congruence closure is, it's basically a, a proof rule to decide validity in this theory of uninterpreted functions. So it basically says that if you have ground terms t1, t1 prime, which are equal, and t2, t2 prime, which are equal, and so on, then it must be the case that the terms f of t1 through tk and the term f of t1 prime through tk prime are equal. And the way you interpret this is to say is the following. You say that, so basically in every structure M, if the values corresponding to t1, t1 prime are equal and t2, t2 prime are equal, etc., then it must be the case that the value associated with f of t1 through tk is equal to the value associated with f of t1 prime through tk prime. Okay, so that's a pretty intuitive proof rule. Okay, so now I want to talk about how do you do congruence closure on executions, or rather, what does it mean to do congruence closure on executions? So let's take this execution, for example. So here you're assuming x equal to y in the beginning, and then in this new variable x1, you're storing the value of f of x, and then in this new variable y1, you're storing the value of f of y. Okay, so as you can see, congruence would mean that x1 and y1 are also equal whenever x equal to y holds. Okay, and I would like to deduce this this fact using congruence closure on this execution. So initially, you have two variables x and y, which are shown in these square purple boxes, and they're associated to these terms x hat and y hat, which are basically ground constants in your vocabulary. And then when you see the statement x equal to y, you mark them equal. So this is how I will mark things equal. And then when you see this computation, x1 is assigned f of x, you create a new term f of x hat, and then you label it with x1. And then on the next assignment, you create a new term f of y hat, and then you label it with y. And so if you ask this question whether x1 and y1 are equal, well, they are, because of congruence closure. And that's because if x hat and y hat, which are ground terms, are equal, then f of x hat and f of y hat must also be equal. So that's basically what it means to perform congruence closure on an execution. Okay, so I'd like to now look at a bit more involved execution. So here what is happening is the following. So in the beginning, you are assuming x equal to y, and then you're computing you're computing f of x and rewriting it to x. And you do this for n times. So at the end, you have computed f to the n of the original value of x. And now you do the same for y. So you compute y equal to f of y in the beginning, and then you do it n times. And so you would have n applications of f onto the initial value of y. So here again, initially, after this assume x equal to y, you would have marked these two terms, x hat and y hat, to be equal. And at this point in the execution, which is the final assignment to x, you would have computed a bunch of terms, and you would have labeled the last term to be x. Okay, and at the final position here, you would have computed this bunch of terms, y hat all the way to f to the n y hat, and you would now label y to be this last term. So again, if we ask this question whether the value of x and y are equal, well, they are, again, because of congruence closure, because if you do x hat and y hat, if you deem them to be equal, then these successive terms are equal. And then you can apply congruence again, and then you will get that each of these corresponding terms are equal. And at the end, f to the n x hat and f to the n y hat are also going to be equal. Okay, but what is crucial to note here is that if I'm going to do such a congruence closure in this kind of a streaming fashion, then I'd require unbounded memory. That is because congruence works in step by step, and in order to infer the final equality on these final terms f to the n and x hat and f to the n y hat, I really need to look at all of these intermediate pairs of terms. So I might need to store all of these terms if I have to perform this congruence closure correctly. Okay, so let's also look at this other execution, which is also involved, but it does not have this previous problem. And I'll tell you what is happening here. So in the beginning, you say you have 4 variables, x, y, x1, y1, and in the beginning you assign x1 to f of x. And then in the next step, you assign y1 to f of y. Okay, and then you repeat this pattern. So you keep assigning x1 to f of x1. Sorry, this is a typo. It should be x1. You keep assigning x1 to f of x1 and y1 to f of y1 in sort of tandem. And at the end, you assume x equal to y. So, so as you can see that at the end, after this assumption, x1 and y1 must also be equal. So let's look at how or what happens in this congruence closure setting. So at the end of this last assignment y1 through f of y1, you would have computed all these this chain of terms x hat f of x hat all the way until f to the n of x hat, and the only variables you have are x and x1 here. Similarly, you would have computed y hat all the way until f to the n y hat, and again you only have access to the first term and the last term using these variables. Or in other words, all the intermediate terms are not stored in any variable and they have been sort of dropped or forgotten. So here, if I do this assume x equal to y, as you can see, x1 and y1 should also be marked equal. But again, I cannot really deem them to be equal because congruence closure requires you uh, to have access to all of these intermediate terms, and or rather, if I want to do congruence closure correctly, I need unbounded memory. Okay, so this is basically the secret ingredient for coherence. It lets you it lets you perform congruence closure in a streaming fashion uh, with bounded memory, and that is basically what is going to give you decidability. So let's formalize things a bit. Uh, I'm going to be talking about terms and equalities and disequalities that are accumulated in execution. So the term associated with the variable at the end of an execution is very intuitive. So in the beginning, x is associated with x hat. Uh, if you assign x to y, then x gets the term that is associated with y previously. If you have an assignment of the form x equal to f of z1 through zn, then you get the term which is f of the terms associated with z1 through zn. Uh, okay, so what are equalities and the disequalities that are accumulated? So at every equality assume, you accumulate the two terms that are associated with x and y. Okay, so and that basically, so if you collect all of these pair of terms, that's the set of equalities that you have, term equalities that you have. Similarly, disequalities are the term disequalities are also defined in a similar fashion. Okay, so coherence is a property of executions, and it restricts execution so that they have these two properties, memoizing and early assumes. So what are these two properties intuitively? Well, the first property says that whenever you're doing a recomputation of a term, then some variable must already have an equivalent copy of that term at the point of recomputation. Okay, I'll define it in a more formal sense later. And the second property, early assume, says that whenever you're observing an equality assume, so assume x equal to y, then any super term of x or y that has ever been computed until now must again be present in some variable currently. And again, I'm going to talk about this in a bit more detail. So let's look at the first property, memoizing. So an execution is said to be memoizing if for every prefix of row of the form which ends in an assignment f of y1 through yr, we must have the following property. Okay, so this says that if you have a term t which was previously computed in sigma, so sigma is a smaller prefix, and this term t is actually equivalent to this new term that you're going to compute. So this is the term associated with x, uh, this term associated with x at the end of sigma prime. And if these two terms are equivalent according to the equalities that you've seen until now in sigma, so basically this is a recomputation of term t modulo the equalities. Sorry, my cat is a bit anxious. Okay. Hey. Okay. So yes, I was saying that if you have a term that has been previously computed, and if you're recomputing the term, then it must be the case that some variable z must already have a term that is equivalent to this term. Okay. So basically it says that if you are not essentially recomputing any term, or rather if you are recomputing modulo this congruence of equalities, it must already be present. Okay, so let's look at this program. All executions in this program are memoizing, because you're not really recomputing any term, even modulo the equalities. Okay, and so yeah, so this is also a memoizing program because all its executions are memoizing. So let's look at an example of a non-memoizing execution. So this is the same execution as that we've seen before. So here you were computing a bunch of terms on x, and then you were then computing a bunch of terms on y. Okay, and x hat and y hat were deemed to be equal in the beginning. So as you can see, you have forgotten f of x hat when you were computing f of y hat. Okay, and they were already deemed to be equal at the point of recomputation. So that is not allowed in a memoizing execution. So this in fact was not a memoizing execution, and memoizing executions will not have such a problem. So this is one key ingredient in performing this congruence closure in an efficient manner. Let's look at this execution, which is a slightly different execution. Here I'm assuming x equal to y, and then I'm going to perform these computations on x and y in tandem. So every time I'm recomputing a term, it's already in y, it's already present in x. So this execution is basically a memoizing execution. Okay, now let's look at the second property, early assumes. So what does this say? It says that whenever you're performing an equality assume, x equal to y, then any super term of x and y. So here's the notion of super terms is modulo equivalence. So we say that T1 is a super term of T2 if you can find T1 prime and T2 prime such that T1 prime is a super term of T2 prime, and T1 is equivalent to T1 prime and T2 is equivalent to T2 prime. So that's a notion of super term I'm working with. So whenever you are performing this equality assume x equal to y, and you have computed a super term of either x or y until now, then that super term or some equivalent copy of that super term must already be present in some variable at the time of performing this assume. So these are basically the two ingredients for decidability. So before I move on to the result, let me sort of talk about this second condition. This is again the same execution that we've seen before, where you were performing the computation on x and y in tandem, but the assume was late. And as you can see, this is a late assume because there have been super terms of x and y that have been computed before, but they're no longer in any variable. They have been dropped or forgotten. And so this is not an execution that satisfies this early assume property. On the other hand, this execution where you shift the assume x equal to y right in the beginning, so it's also an equivalent execution in terms of semantics, then this execution does satisfy the early assumes property. Okay, so if you look at this program, which has been with us for a long time now, here, as you can see, the only equality assumes occur because you have exited a loop. So all equality assumes are at the end. And now at the end, so y, there is no super term of y. And also at the end, you have not computed any super term of x. So all executions here are also satisfy this property of early assumes, and therefore they satisfy both memoizing and early assumes property, and they are coherent executions. So this program is also called a coherent program because all its executions are coherent. So let's look at the main result, which is about verification of coherent uninterpreted programs. So let's say we say that a program P is coherent if all its executions are coherent. Okay, and so the main result here is that the verification of uninterpreted coherent programs is decidable, and it's in fact P space complete. So I'm going to spend like 1 or 2 minutes in maybe more on the proof. But the basic idea is that you can come up with a regular language, which is such that it contains all coherent executions which satisfy the assertion phi, which is this language. And then the verification question basically boils down to this containment check. So we have seen before that exec of P, which is a set of executions of P, is regular. And this language is also regular. So this question of containment is decidable. And the complexity follows from the construction of the automaton for L-coherent, which I'll talk next. Do we have a question, or can I move on?
Yeah, I guess you can move on.
Okay. Okay, so let's look at the details of this proof. So I'm going to answer whether P meets the specification phi, and an equivalent question is whether this program P followed by an assume not phi is not true in any model, or it satisfies the formula false. Okay, so then the question boils down to whether the executions of this program do not intersect with a language called L-coherent feasible, which is basically a language which I will construct in some time. And the property of this language is that it contains all coherent executions which are feasible in some first order structure. So what this means is that this program, which should not be feasible in any model, must be disjoint with this execution, this language. Okay, so now let's look at an automaton that accepts this language. So this automaton.
Umang,
yes.
just a minute. We have approximately 10 more minutes. Okay.
Okay, so I should rush. Okay. So this automaton is such that you have a special reject state, and all the other states are of the form are triplets of this kind. So the first component maintains equality relationships between variables. Okay, and that is the salient feature. This automaton does not look at terms as such. It just looks at variables and relationships between them. And it so happens that just maintaining the relationship between variables lets you do congruence closure in a streaming fashion. So the first component maintains whatever equalities that you can infer between variables. So for example, x1 and x3 are in the same class, x2 and x4 are in the same class, etc. The second component tells you what all disequalities have been assumed until now. Okay, and again, we are only going to maintain this relationship between the values, the current values of the variables. Okay, we are not going to talk about any terms. We're not going to talk about any values that have been forgotten or overwritten. We're only going to talk about the current values, the current variables. And the last component essentially maintains how equivalence classes are related using functions. So f on either x1 or x3 maps to x2 or x4 or x5. Okay, so these are equivalence classes, so it's essentially the same. Okay, so what are transitions here? So transitions let you update these relationships in a inductive streaming fashion. So let's look at an example here. So let's say initially x1, so you have 4 variables in the program, x, y, x1, y1, and initially x1 is assigned to be f of x. So that is how the state would look like. You will have x, y, x1, y1 in their own individual equivalence classes. And after this assignment, you would point this f from x to x1. So when you do y1 equal to f of y, you would point y to y1 using f. And when you see this assume, you would put x and y, the variables x and y in the same equivalence class. And then congruence closure would tell you that uh, you can also put x1 and y1 in the same equivalence class. And so when you see this assume x not equal to y, so sorry, this should be x1 not equal to y1. When you see this assume x1 not equal to y1, you can already say that they're in the same equivalence class and therefore you must reject. So this is in fact an infeasible execution. So that's how intuitively the automaton works. Okay, I will probably not talk about the correctness, but intuitively it says that if you have a feasible execution, if you have an infeasible execution, then you go to reject state. And if you have a feasible execution or feasible in any model, in some model, then whatever state you reach, the relationships on variables that you are storing in your state essentially reflect your equalities that you've seen until now and the disequalities that you've seen until now, and also the functional relationships that you've constructed until now. But let me go to the next next slide, which is about checking coherence. So we also show that you can check whether a program is coherent uh, because you can again do a similar automaton construction. Okay, so checking coherence basically asks if a program P is such that all its executions are coherent. And this question is also decidable. I'm going to skip the details, but it is the construction, the automaton construction is pretty similar to the one that we've seen. Okay, so let's look at this property called k-Coherence. And to motivate that, I'll say that if you look at this program, you'll realize that this is not a coherent program because here you're recomputing. So here y was associated with this term n of x hat. And now you have overwritten this value in y. And now you're recomputing it here again. And when you're recomputing, this original value of n of x hat is no more there in any variable. So there's a recomputation because you don't have enough variables. If you had enough variables, you would have stored them. And that is the reason why this program is not memoizing and therefore not coherent. But this program can be made coherent. And this can be made coherent by adding these auxiliary ghost variables, G, and assignments to these variables. So these are ghost write-only variables. And when you do that, you can see that this term n of x hat is present at the time of this recomputation. And in fact, in every later recomputation. So because I can add one variable and assignments to this variable, I will say that this original program was one coherent. So in general, you can extend this to k-Coherence, which basically says if you fix a k, which is a natural number, and you're allowed k extra variables, which are ghost write-only variables, then an execution is k-coherent. An execution of a set of variables v is k-coherent if you can annotate it with the assignments from these assignments of this kind. G is a ghost variable and X is a regular variable. So if you can annotate this variable with assignments of this kind, so that the resulting execution is coherent, then the original execution is said to be k-coherent. And a program is said to be k-coherent if all its executions are k-coherent. So we show that, in fact, both checking if a program is k-coherent and also verifying a k-coherent program is again decidable in p-space. Again, I'm not going to go into the details. Okay, so with this, let's move on to the next segment, which I think should be quick, of verification modulo theories. Okay, so until now we've seen uninterpreted programs, and I told you that they are a nice abstraction because you can abstract the semantics, the interpretations of all your symbols, and you can think of it as an uninterpreted program. And if you can prove it correct, then the original program is also correct. But sometimes you do need interpretations to prove correctness. So here is an example. Here I'm computing the minimum of 3 elements A, B, C. I'm first checking if A is less than B, and if so, then I'll check A less than C, and then assign min equal to A, and so on. Okay, and so the post condition is whether min is less than A, less than B, less than C. Okay, so in fact, this condition does not hold in every model. So here is an example. Here's a counter example. This is a model where you have three elements: A hat, B hat, C hat. A is initially associated with A hat, B is associated with B hat, and C is associated with C hat. And the interpretation of less than equal to is basically cyclic. So A is less than B, B is less than C, and C is less than A. Okay, so because this is an arbitrary relation, it's not a total order, and that is why this program, which is only meant to work over total orders, will not work on this model. Okay, so in fact, this post condition will hold in every model in which less than equal to is a total order. And in fact, you do need to have this interpretation if you want to prove this correct. So the next natural question that we ask is, if you have a program P, and if you have a set of first order sentences A, which are axioms or a theory, then what does it mean to say that P satisfies phi modulo A? This question basically asks if for every execution of the program and for every model M such that M satisfy all these sentences in A, and is also such that rho is feasible in M, then the post condition holds at the end of every such execution. So this is the question of verification modulo theories, and we have to slightly modify the definition of coherence to fit this new notion of modulo axioms. And let's look at this example. So here I have this theory where the function f is commutative, and so in this execution, where I'm first computing f of x comma y, and then I'm computing f of y comma x, then this is really recomputation if you think modulo commutativity, because these two terms are equal modulo commutativity, and so x1 and y1 are equal, and therefore there's a recomputation that is happening here. So that is one of the complications that you have to deal with when you have to do modulo axioms. Similarly here, what I'm doing is I'm computing f of xy, and then I'm computing f of y comma x prime. So this is different from this. And then I'm computing a super term of x1, and then I'm computing a super term of y1. And then at the end, I'm going to say x equal to x prime. So here, if you do assume x equal to x prime, then these two terms, z and z prime, are also implied to be equal because of the commutativity axiom. So this is the second complication that you have to deal with. And so there is a very intuitive definition of memoizing modulo axioms and early assumes modulo axioms, which I think I will not go into for the sake of time. And I'd like to conclude by saying that we studied a bunch of axioms. So some of them are relational axioms, some of them are functional axioms, and in the most general form, when you have, let's say, an axiom which lies in this EPR class, or effectively propositional logic, or Burnett-Schonfinkle class, then even verification of single executions is undecidable. So that is why you cannot get decidability. But for most natural axioms that you would like, you do have decidability. So if your relations are reflexive, or irreflexive or symmetric, or their total orders, then verification modulo these axioms is decidable. Similarly, if you have functions which are commutative or idempotent, then again, it is decidable. And if your functions are associative, then even verification of a single execution is undecidable. And finally, we show that if you have any combinations of the decidable axioms, then you also get decidability. So with this, I'd like to conclude, and I'd like to take on questions.
Okay, so thank you, Umang.
Thank you.
So I'll request everybody to unmute themselves and thank Umang.
Because now I have the key, so I will also come to the Spy Lab on some days.
Okay, so send Aurora an email asking to go. I think the Spy Lab is empty, no?
Yeah.
Okay.
So can we all thank Umang before
Fine,
we go on to the
Spy
questions?
Lab, there are more than 4 people.
And then
Okay, so be careful. Okay.
I get sick very quickly, so I try to be more careful.
Okay, so now if you have a question, I'll request you to use the raise hand feature. Okay, maybe, yeah. So I see a question from Sparsha. Yes, Sparsha, so please unmute yourself and go ahead.
Yes, so I have a question on, so you already said that given a program, we can check if it is k-coherence in p-space complexity, right? Hello?
Umang, you have to unmute yourself. Umang.
Yes, that's right. So you can check if a program is k-coherent in peak space.
Okay, so suppose I have given a program, arbitrary program, and we don't know if it is at all coherent by any k. So is it undecidable to find a particular value of k for which it will become some k-coherent?
Well, yes, because every program will be coherent. Well, I don't know. So we didn't look at this question, and I don't know if that's decidable. Yeah, I don't know.
Okay, I see. Okay.
Okay, Parosh has a question next. Parosh, please go ahead, unmute yourself.
Yes, hello, Umang. Very nice presentation.
Hi, Varesh. Thank you.
I have a question. So if you look at the case where you have uninterpreted function symbols, so you can see it as an over-approximation of the interpreted case because you allow more transitions in your system. And this works because this is a sound over-approximation with respect to safety properties. I mean, you are checking assertion violations. So my question is related to liveness. So this would not work for liveness properties. Is that correct?
You mean the abstraction?
Yes. So if you give me a program with interpreted function symbols, like I have plus and minus, and I replace them by uninterpreted function symbols. Now, if you show that you will not violate a given assertion, this will hold in the original program also, because you are doing an over-approximation.
Yes.
But for liveness, this would not work, because having such an approximation may, I mean, it need not be sound with respect to liveness. But anyway, so can you check liveness properties for this class of programs, or have you thought about this?
Well, so this decision procedure is automata theoretic. And so I guess it will be, if you have, let's say, a LTL property or a CTL property, I think you can check it. It's going to be decidable for coherent uninterpreted programs.
Oh, that's okay. Thank you.
Thank you.
Okay, Nikolai, go ahead.
I have 2 questions.
Yes.
One just terminological and historical.
Okay.
Well, why to speak about uninterpreted programs instead of very classical 20 years ago term program schemata? At least some great people use this term in the past.
Yeah,
like
so
Manna and Noel, for example.
Okay, so yeah, so in fact, I was told about this very recently, and thank you. So can you tell me what is the reference that I should look at?
I can send you.
Sure.
I will send you since I know how to contact you. I'll send you. Don't worry.
Okay.
Another question is, well, To the best of my knowledge, in theory of program schemata, that is, in theory of uninterpreted programs, the strongest decidable equivalence is so-called logic and thermal equivalence. Logic, it is also polynomially decidable. Well, do you know what about if to consider program uninterpreted programs up to logic and thermal equivalence? What in this case you can say about decidability of verification problem?
So what does it mean to say that
Logic and thermal equivalence?
Yeah.
Again, I believe that it is not right time to explain details.
Sure.
I'll
Okay,
send
so
you reference. I'll send
Okay.
you reference.
So
Okay.
thank you.
Thank you. Nevertheless, thank you very much for your talk. It is definitely related.
Thank you.
I'll
Okay.
contact you. I'll contact.
Yeah, thank you, Nikolai. So David, you can go ahead now.
Hi, so this is maybe a slightly technical question, but you started by reducing verification of phi to non-termination of p superscript not phi.
So not non-termination. So I'm only looking at terminating executions.
Yeah, but you reduced it to saying that p not phi has no terminating executions, right?
Sure. Yeah. Yeah.
So can it happen that p is coherent, but p not phi is not coherent?
That is right. So in fact, yes, you're right. In fact, there is a slight technical glitch, which I let it be because I wanted the presentation to be easy. So you're right that you really want that. Where am I? You really want that this program p not phi is in fact coherent. In fact, it can happen that some assume because of this is late. It's not early.
Sorry, so the theorem is actually false, is it? It's not true that if p is coherent, then...
That's right. So you also need special kinds of assertions. Yes.
Okay, so Umang, I had a question also related to. Okay. So before I go, Dexter, please go ahead.
Thanks, Umang. Nice talk.
Thank you.
I was wondering if these conditions that you came up with, coherence and early assertion, are necessary and sufficient for some automaton that would otherwise have infinitely many states to only have finitely many states. Does that question make sense?
So it does. Yeah, sure. Go ahead.
No, go ahead.
Okay, I can probably give you the following answer, which I don't know if is the right answer, but so if you have a program which is just memoizing, then the verification for this class is also undecidable. Or if you have a program which just satisfies early assumes and not memoizing, then the verification of that class of programs is also undecidable.
Sure, you need both conditions, I guess.
You need both, yes.
Yeah, and also for the other one too, I'm sure. I mean, if you just assume early,
yes,
early
both.
assertions, that's also
right.
undecidable. Okay.
Yes, yeah.
Okay. Yeah. So the question is, can you phrase the result in the following terms? You have you look at the traces that the program generates, and there's some kind of infinite state automaton that you can't get through all the states to do the verification you need to do. But with those two conditions, it collapses that automaton to a finite state machine.
That's right. So I think that is right.
Okay.
Yeah. Basically, you will accumulate all terms in your executions, and
Okay.
you would mark them to be congruent or not.
Gotcha. Great. Thanks.
Thank you.
Okay. So Nikolai, yeah, go ahead.
Thank you very much for one more opportunity to ask a question. What if to define dynamic logic for coherent programs? Will it be decidable?
I don't know about dynamic logic, so yeah, it'll be great if you can send me some pointers to that also. Yeah.
Okay, I will send
Sorry
you.
about that.
I believe Dexter can say something.
Yeah, there's a book, I think, somewhere.
Right. But I will contact you. Mhm.
Okay, thank you.
Okay, so do we have some more questions? Okay, fine. If nobody else, so Umang, so what I was wondering is, I guess this notion of coherence seems to be really crucial for getting decidability, and so of course this is sequential programs, but so what is not clear is if I go to concurrent programs under sequential consistency, or say any of the weak memory models, this definition of coherence probably may not help you to regain decidability. Is that correct?
That is right. So in fact, there is also some recent paper in FSTTCS, I believe 2019,
I see.
by Madhusudan and Salvatore, where
Okay,
they study this question. In fact, they do restrict coherence even further.
Oh, I see. Okay, so what would that mean? So restriction in so you do need memoization and this early assumes, but you need something more top for the concurrent case.
Yes, yeah. I'm not entirely sure, but yeah, they do have some results there. Yeah.
Okay, but this is for sequential consistency.
That is for sequential consistency. Yes.
Okay, so in some sense, so the case of weak memory models has not been explored yet. Is that right?
No, I don't think so. Yeah.
Okay. Fine. Okay, so maybe I guess we don't have any more questions. In that case, can we all thank Umang once again for a wonderful talk?
Thank you.
Oh, I see one more question. Oh, okay, that is not a question. It's a clapping, applause from Vrunda. The semantics of the raise hand and the clap is still confusing for me, unfortunately.
It should be different colors.
Yeah. Okay, great. Okay, so thank you very much. And if you would like to stay for the coffee break, you are most welcome. Otherwise, maybe you could leave.
Can I stop sharing my screen?
Yep.
Yeah.
I guess. Sorry.
Is it already stopped?
No, I can still see, I think.
Okay.
It is stopping.
Stopping. Okay. Oh yeah, I know what you mean. So stop share. Okay.